This paper shows how to find sums of powers of roots of polynomials using the Transpose and Apply sutra of Vedic Mathematics. A polynomial, as you probably know, is simply a power series in an unknown. For example, here is a quadratic polynomial, x squared plus 3x plus 2. Here's another polynomial, which is a cubic, power of 3. The highest power of x is 3, so it's called a cubic. So this is a quadratic, which has 2 roots, or zeros, and this is a cubic, which has 3 roots, or zeros. What do we mean by zeros? Well, they're the values of x that will make this expression come to 0. The zeros of this quadratic are the values of x that make it come to 0. In that particular case, it's -1 and -2. They will both make it come to 0. And so -1 and -2 are the roots, or zeros, of that quadratic. Similarly, for higher powers, a cubic has 3 roots, and they're the values of x that make that come to 0. And for higher powers as well, 4th power, 5th power, and so on. Now, in chapter 22 of Tirthaji's book, he explains an interesting connection between the factors of a polynomial and its first differential. So I'd just like to explain that here. Suppose we've got this quadratic expression, which actually factorizes like this. The sum of those factors is found by obviously adding them up, and we get 2x plus 3. That's the first differential. So the sum of the factors is the first differential in the case of a quadratic. A similar thing happens for a cubic. This particular cubic factorizes like this, x plus 1 times x plus 2 times x plus 3. And if we take the sums of the products of the factors taken 2 at a time, that means we take either the first pair or the last pair or the 2 outer ones, like this. If we take the first pair, the product comes to this. If we take the last pair, the product comes to this. And if we take the product of the first and last, we get this. When we add those up, we get 3x squared plus 12x plus 11, which is the first differential. If you differentiate this expression, you get the sum of the products of the factors taken 2 at a time. Tirthaji explains this in chapter 22, and he says it comes under the sutra Gunaka Samuchaya, sutra 16, which translates as all the multipliers, or in our case here, all the factors. So here we've got all possible products of factors taken 2 at a time. This result is proved formally in my paper, and of course it applies to higher power expressions as well. So if you've got a 4th power, a quartic expression, then you will need to find the sum of the products of the factors taken 3 at a time. So in general we can say that the first differential of a polynomial of degree n, the degree is the highest power of x in the polynomial, in which the leading coefficient is 1, the coefficients of the x cubed and the x squared here are 1, is the sum of all the products of its factors taken n minus 1 at a time. So this paper shows a use of this result. Suppose we take this quadratic here, x squared minus 3x plus 2, which factorizes like this, x minus 1 times x minus 2, and it has roots 1 and 2. If you put x equal to 1 or 2, you get 0 for that quadratic. Now suppose we require the sum of the roots, which is obviously 1 plus 2 is 3, but this is just a simple example, and we might require the sum of the squares of the roots, the sum of the cubes of the roots, and so on. We can get these results very easily, as I'm going to show you. Suppose we take the quadratic expression and we divide it into its first differential, 2x minus 3. One thing we could do with that is to divide the denominator into the numerator using the transpose and apply formula. So here it is set out in the usual way. So we transpose the coefficients in the divisor and we get plus 3 and minus 2. We then divide the first by the first. 2x divided by x squared is 2 over x. And then we multiply the coefficient there by the 2 transposed values and put them in the next 2 columns. So 2 times plus 3 is plus 6. 2 times minus 2. 2 times minus 2 is minus 4. Then we add up in the next column. We get 3. So we have 3 over x squared in the next place. And the powers of x are going down by 1 each time, as we've got in the divisor and the dividend here. So we get a 3, and we multiply that 3 by the two transposed figures. 3 times plus 3 is plus 9. 3 times minus 2 is minus 6. Add up in the next column, we just get a 5 there, so we've got plus 5 over x cubed. Then we take the 5, multiply it by the transposed digits, and we get plus 15 and minus 10 in the next two columns. We add up in the next column there again, and we get 9. So 9 over x to the 4th, and we can continue like that. Now, before we explain what the use of this is, let's do this a different way. Instead of dividing like that, what we're going to do is to rewrite this fraction in a different way. You know the top is the first differential of the quadratic, and the first differential is the sum of the factors. So there's the sum of the factors, x minus 1 and x minus 2. And the bottom is, of course, the product of the factors, x minus 1 times x minus 2. Now, we can split this up into two separate fractions, the x minus 1 over that product, plus the x minus 2 over that product. And if we do that, we find that in the first case the x minus 1 cancels and leaves us with 1 over x minus 2, and in the second case the x minus 2 cancels and leaves us with 1 over x minus 1. What we're going to do next is simply divide these using the transpose and apply formula, like we did over here. So we're going to divide x minus 2 into 1, and I'm going to do it over here in this box. So x minus 2 is divided into 1. So we first divide we first of all transpose the minus 2 to a plus 2. Then we divide the first by the first, so we get 1 over x. We multiply the coefficient thus obtained with the transposed figure, so we get plus 2 in the next column. So in the next column we just got a plus 2 over x squared. We continue like that, so the 2 there times the 2 is plus 4. Add up in this column we just get 2 squared over x cubed, because the 2 has multiplied the 2, so we've got 2 squared. And carrying on like that, the next term will be 2 cubed over x to the 4th, and so on. So we bring that result over here, and we do the same thing for the other fraction, 1 over x minus 1. So we're going to divide x minus 1 into 1 in just the same way. Transpose, divide the first by the first to get 1 over x. 1 times the plus 1 is plus 1. Bring that down, we get 1 over x squared. 1 times 1 is 1 in the next column. Bring that down, we get 1 over x cubed, and so on. The next one will be 1 cubed over x to the 4th. We bring that over here, and this is what we've got. Now we can combine like terms together, so we've got 1 over x plus 1 over x, which is 2 over x. The x squareds in the denominator there, those two can be combined. So you've got 2 plus 1 over x squared, or 1 plus 2 over x squared. And then the x cubed, you're going to get 1 squared plus 2 squared over x cubed, and so on. Now the result that we've obtained here is the same as the result we've obtained here. Obviously it started off with the same fraction, the results must be the same. And this actually shows what we can see quite plainly, that the 2 is just the number of roots, the 3 is the sum of the roots, there they are, 1 plus 2, and the 5 is the sum of the squares of the roots, 1 squared plus 2 squared, and the 9 is the sum of the cubes, and so on. And so what all this means is that instead of going through all this here on the right hand side in order to find the sum of the squares, sum of the cubes or whatever, we can simply divide a quadratic into its first differential, and the coefficients we get give us what we want. So let's take another example to illustrate. So what I've done, the quadratic had simple roots there, 1 and 2. But the quadratic may have irrational roots, or it may have complex roots. But the method works just the same. So x squared plus 5x plus 2 actually has irrational roots. And suppose you want to find the sum of the cubes of the roots. All we need to do is to divide the quadratic into its differential, like this. So there it is set out. We transpose the values of x, we get minus 5 and minus 2. We divide the first by the first, we get 2 over x. We multiply the 2 by those transposed figures and put up minus 10 and minus 4. We add up in the next column, we get minus 5 over x squared. We multiply the transposed figures by that minus 5, giving us 25 and 10. Add up in the next column, we 21 over x cubed. Then multiplying the 21 with the transposed figures, we get minus 105 and minus 42. And then adding in the next column, we get minus 95 over x to the fourth, and so on. Now we want the sum of the cubes of the roots. So we know that's the number of roots, the sum of the roots, the sum of the squares. This will be the sum of the cubes of the roots. So the answer is minus 95. Now if you do this by the long way, by actually finding the roots of that quadratic and then finding the sum of the cubes of those, it would take you a long time. This is a much easier and quicker method. And in fact it can be simplified because these little numbers here in blue can be left out. I'll show you how to do that. We're going to use the vertically and crosswise sutra. Sutra 3. So we mark the transposed figures like that, and we divide the first by the first as before, 2 over x. Now we mentally multiply the coefficient there by the first transposed digit and add it in the next column. So we have minus 10 when we multiply those. We add it on here, we get minus 5. Now we take those two coefficients and cross-multiply them, this is vertically and crosswise, with the transposed figures. So it's the minus 5 times the minus 5 and the minus 2 times the 2. So we get 25 minus 4, which is 21. That's the 21, we had that before. And we can continue like that. So the next step will be to multiply the minus 5 and the 21 with those. So minus 5 times 21 is minus 105. And minus 2 times minus 5 is 10. The minus 105 with 10 added is minus 95. So we get the same results as before. And that's a quicker method. Now let's take a cubic. Here's a cubic, and in fact it has roots 1, minus 3 and 4. So you can check the results when we get them, but it applies to cubics that have irrational roots or complex roots as well. So we're going to do the same thing as before, which means we're going to divide the cubic into its first differential. So there's the cubic, there's the first differential. There's the division. We transpose the coefficients here. The minus 2 becomes plus 2 and so on. We divide the first term by the first term. 3x squared divided by x cubed, that's 3 over x. Then we multiply those transposed figures by the 3. We get plus 6, plus 33 and minus 36. We can do it without these figures, but I'm just making it clearer, I hope, by including them at the moment. So next we add up in this column, we get 2 over x squared. Then we multiply 2 by each of the transposed figures, so 2 times plus 2 is 4. These go in the next 3 columns. 2 times 11, and 2 times minus 12. Add up in this column, we get 22 and 4 is 26. 26 over x cubed. Now we multiply the 26 by those transposed figures and put them in the next three columns. So we have 52. Then we add in this column, we get 38. So 38 over x to the fourth and so on. So according to our scheme, this 3 here is the number of roots, the cubic, which we know is always 3. There they are, in fact 3 there. The next one is the sum of the roots. Well, we can check that by just adding up here. Yes, if we add these numbers up, we get 2. The 26 should be the sum of the squares. So what have we got? 16 and 10 is 26. That's right. And then the sum of the cubes will come to 38 and so on. So we very easily got the results here simply by division with transpose and apply. I'll just do it once more without the extra work. The transpose figures are there, and we do the first by the first as before. So 3x squared divided by x cubed is 3 over x. Then we multiply the 3 by the 2 to get 6 and add it in the next column. That gives us 2. Now we cross multiply the two coefficients there with the first two transposed figures. So that means the 2 times the 2 and the 3 times the 11. So we've got 33 and 4. 37 minus the 11 here gives us the 26. You see we're getting the same answers as before. And the next step will be to cross multiply those 3 coefficients with the 3 transpose values, and you would get 38. So this can apply to all cubics and to higher power polynomials as well. There is a formal proof in my paper of this, but I'm just going to prove it for cubics here, for this particular cubic and for cubics in general. So we know that that cubic has got roots 1, minus 3 and 4, and it's got factors as shown here then. And if we divide the cubic into its first differential, we'll be dividing the cubic into the sum of the products of factors taken 2 at a time. That's the first 2, that's the first and last, that's the last 2. And what we can do here is, as before, we can split this up into 3 fractions. So it's the first product there over this denominator, plus the second product over the same denominator, and the third. Then we can do some cancelling, and we simply get this. And then we can divide. We get this, this, and this for the 3 divisions. And we can combine like terms. So we've got 1 over x plus 1 over x plus 1 over x is 3 over x. And then we get, for the x squared denominator, we get 4 minus 3 and 1 over x squared. And then the sum of the squares over x cubed and so on. Actually, this can be understood as a proof of this method for cubics, because we haven't actually done any calculations with the minus 1, 3 and the minus 4. So we can imagine that instead of x minus 1 we've got x minus a, and then here we could have x minus b, x minus c. And we could follow that through with the a's, b's and c's, and we'd end up with the same result here. That this is the sum of the roots, this is the sum of the squares of the roots, and so on. As I said, you can see my paper for a formal proof for all polynomials. One more variation is that if the leading coefficient is not unity, here it's a 2 instead of a 1, then the same method can be used. You can divide the polynomial into its first differential, and the coefficients you get are the sum of the roots, the sum of the squares of the roots, and so on. The reason that would work is simply that if you do get a quadratic or polynomial where the leading coefficient is not 1, you can divide it through by that first coefficient. So in this case we could divide the top and bottom of this fraction by 2, and the top will still be the first differential of the bottom, and the roots of the polynomial will be unchanged. So let's do the division, and let's do it in one go. So the transposed figures are +7 and -3, and the difference between what we've been doing before in the division and what we're going to do here, because of that 2, is simply that at each step after the first we divide by that coefficient of x squared, 2 in this case. So we begin by dividing the first by the first. 4x over 2x squared is 2 over x. Now we multiply the coefficient by the first transposed figure and add on the next number and divide by 2 because of this 2 here. So we have 2 7s are 14, add it on here gives us 7, and then dividing by 2 gives us 3.5 over x squared. Continuing, we cross-multiply those coefficients with the two transposed numbers. So we'd have 7 times 3.5, which is 24.5, and here we have -6, so we get 18.5, and then we have to divide by 2, which gives us 9.25. And we continue like that. So the next step will be to multiply these two coefficients with the transposed figures and divide by 2. So what we found here is that there are 2 roots to this quadratic. The sum of those roots is 3.5, and the sum of the squares of the roots is 9.25, and we could go on if we needed to. So that's it. The Transpose and Apply sutra then gives us an easy way to get sums of powers of roots of any polynomial by simply dividing the polynomial into its first differential and noting the relevant coefficients. And the work can be simplified using the vertically and crosswise formula on the transposed values and the coefficients as they arise.